programming for wind energy. So here's the agenda for today. So first we will do a welcome and introduction, and then we'll follow by a presentation by Zhu Feng and Jenny, and after that we will do a Q&A section. So if you have any questions, you're welcome to write in the chat, and then after the presentation we will answer your questions. So as I told you before, my name is Alan. I'm a head of study for this program, and also I'm an associate professor at DTU Wien. And today we have Zhu Feng. Zhu Feng is the course responsible for the scientific programming for wind energy, and he's also a senior researcher at DTU Wien. And together we have Jenny, and Jenny, she's also an associate professor at DTU Wien. And before we go to the presentation, I want to show you the courses we offer on the online master. So for this spring semester, so for the autumn semester, we are offering 7 courses. So as you can see, we have courses from wind turbine design to and also we have like a big scale wind resources courses, and also we have courses on offshore wind energy, so about floating turbines. And as you can see, we also have a new course about scientific programming. We also offer courses in the spring semester next year, and we also have a range of courses. And keep in mind that you can also you can choose to take the entire program. So that means 9 courses plus the final project, but also you can choose the one you are interested. So you don't need to complete the entire program. It's quite flexible. So so that's everything I want to say about the program. Maybe I stop sharing my screen. So Zhu Feng and Jenny, whenever you're ready, you can share the screen.
Yes, thank you, Aaron, for the introduction. And I will share my screen now. Goes to the slides. Yeah. I will change the view. I hope everyone can see the presentation now. No, it's not presenting. Now it's presenting.
Yeah,
Yes.
we can see it now.
Yes, so good afternoon, everyone. It's a great opportunity to present this webinar or masterclass about the scientific programming for wind energy. So this is the outline of today's webinar or masterclass. Before we go to the actual coming online course, which is called Scientific Programming for Wind Energy, we will go through some background and talk about the other things. First of all, we want to introduce ourselves again. So my name is Zhu Feng. I'm a senior researcher in DTU Wing. I'm in the section called System Engineering and Optimization. So my research is focused on wind farm design, layout optimization, also wind farm control. And I have been also involved in development of open source or closed source tools for wind farm design, like Highway, Top Farm, and also FarmWalk, other tools. And regarding programming, Jenny and I also are teaching another Master of Science course, which is also called the Scientific Programming for Wind Energy. Yeah. So Jenny, you can also introduce yourself.
All right, thank you very much. So yes, my name is Jenny. I'm an associate professor here at DTU Wind. I'm in a section that has recently been shuffled around, so the website might not be updated, but the title of my section now is Turbine Response. So the areas of expertise I have is kind of core mechanical engineering, so loads and dynamics. How do you model the physics of wind turbines? How do you simulate them? kind of interactions between turbulence and how that ends up affecting the dynamics of the system. And the kind of experience that I have with programming is a little bit of blend of a fair amount of open source tools. I've also contributed to some reference wind turbines, so the IEA 15 megawatt as well. And yeah, like Dufeng, we teach this scientific programming course for master's students in the spring semester. And then I'm a co-instructor for this online master course. And outside of DTU, I'm also part of a summer school in advanced scientific Python programming. So, and also have been working a little bit on some closed source tools, but primarily open source. Yes, and I'm also happy to be a part of this masterclass.
Yeah, thanks. So of course, today the topic is not focused on specific wind farm design or turbine load, but more on the general kind of scientific program or computing, right? Which is essential. So before we go to the programming part, but we can kind of look at the digitalization, big picture, right? Which we are also working in this project, which is called DigiWin. Stands for Digital Masters for Wind Energy Systems. It's a EU-funded project, but it's specialized for education. Education with regards to digitalization skills for the wind energy sector, right? Both Master of Science, Master, and also lifelong learning for industry. As we all know, in this era, digital era, and we have a lot of the requirements that different jobs will require different kind of digitalization transformation, especially for the wind energy sector. So as you can say here, the quote from, yeah, the industry, it tells about the lead. We really need the digital skills, but usually it's not fully covered in the traditional kind of a wind energy education or mechanical engineering education, right? So in this project, we also identify the kind of four core field, which is HPC, high performance computing, artificial intelligence, cybersecurity, and also other emerging technologies. But we think across all these different fields, we think programming or scientific programming is a foundational, which is kind of critical for all these different fields. So let's kind of our view. We view programming as a foundational digital skill. Everyone should know. And the reason is that in this time, we have found that writing code to be able to write code to solve complex problems that can be in scientific and engineering problems is really becomes more and more important, both for scientists and engineers, right? And so it's also kind of foundational for building other digital capacities. Like if you want to use AI or HPC or other things, you also need to know programming. So in a sense, we think it's not just for computer scientists or programmers to do the programming part, but also engineers should know how to program. So that's why we emphasize this. But a lot of our students also, you may ask the question, we are now in the era of artificial intelligence, like the large language model, like ChatGPT and DeepSeek, or all the other large language models. They can really do amazing jobs to generating code for some stuff, right? So you may ask, does AI change the future? Do we still to learn actually program ourselves, right? If AI is going to do all the coding, why should we learn? So instead of my answering the question, I want to cite a quote from a famous kind of a pioneer in the field of machine learning, which is Andrew. And he was a professor in Stanford and also the founder of Coursera, which is the most popular work platform. And he is specialized in deep learning, different machine learning, also education, right? So he recently made an X post that he mentioned specifically mentioned about why should we still learn programming. You can check the link and to see his full post, but here I want to highlight several points. First, he said that discouraging people from learning programming just because AI will automate it, that's the worst career advice you could give. Because telling a computer exactly what you want will be crucial skills in the era of AI. If we think about it, what is the essence of or what is essence actually when we do programming? We're doing exactly the same thing, right? Telling a computer what do you want, step by step, doing this computation, step 1, step 2. This is programming itself, right? But now if you're just using AI, you still need to tell AI exactly what you want. So you're just programming in a different level. And also coding or learning to programming is the best way that we can develop this skill. And yeah, also, so he made this kind of comparison. Everyone can use DeepSeek, ChatGPT, and generating some code. But in order to get the best out of the AI, you need to know the language software. If you are expert yourself, you have experience in programming software development, then you could better ask a question through the AI and get much better results out of AI. So that's why we think learning programming is still very important in this era. And also, if you watch some recent trends, there's this term called vibe coding, which become very popular. Essentially, it's just the way that you just talk or chat with ChatGPT or any other large language model, and then ask the AI to generate the code, right? But the other way is, I think a lot of people we have experience with, if you are using Copilot or some other things, right? Some other tools, it's kind of AI will assist you in the programming process, right? So vibe coding, although it sounds very kind of promising, but currently there is a lot of risk because if you don't really understand what the AI generates, if you just trust what get out of the black box, you fall into the danger that you will run into bugs that you don't understand. You have low ability to fix that. If you know better programming, if you have more experience, then you will be much better in a much better position to be able to ask AI to assist you, to help you with the whole process. So that's kind of our view. We think everyone will use AI, of course, in the future, but in order to better use AI, we still, and we could even say it becomes more important to know programming. So in wind energy, in the domain of wind energy, we use computation or simulation a lot. If you check the kind of the challenges in the science of wind energy, we need to do a lot of modeling, simulation from different scale, like from the material, through the component, to the turbine, to the farm, to the whole wind farm cluster, and also the interaction with the environment, like the atmosphere, the ocean, also with the grid energy system. Everything is such multidisciplinary, also multi-scale kind of a process. We're trying to simulate, we're trying to design, we're trying to improve, right? So in different ways, we always need to do a lot of computation, a lot of scientific programming is really critical to tackle all these challenges. So, but the reality is that when we really have this lead, we also need to be able to write good code, right? In order to do this, to tackle all these challenges, to be able to model and simulate different aspects of the wind energy systems. If you check kind of in software engineering, what we are trying to tackle here, right? Writing code, write a simple code may be easy, but if you're trying to write a software or piece of a long enough kind of code to tackle a complex problem. That can be challenging. The main challenge in software engineering, actually, I like this quote a lot, which says, managing complexity is the most important technical topic in software development. That means that in different level, different aspect, we need to manage all this complexity, which may come from physical phenomena we're trying to model, we're trying to simulate, but it also comes from the fact that a complex software will have different components. They have very complicated interaction between them. So all of this needs to be managed properly. And the good programming practices and the software engineering practice will help you to manage this kind of complexity, right? So if we ask a basic question, you may also think in your mind of yourself, right? What is a good program? If you write a piece of code doing something, then how do we quantify? Do we say this is good or this is not so good? In our view, we think a good program should do three things at least. First, it is to do the job, right? We write a code or write a program to do something. It could be compute some values, simulate some process, or do some optimization. So the first thing it has to do is to do the job right, get the right value, right output. But just do the job itself is not enough. The second requirement, the program or the code has to be easy to understand, because the program right will be reused, will be extended, will be maintained by ourselves in the future or by our group co-workers, colleagues, our collaborators, and also it will going to be read by ourselves maybe in 3 months in the future, right? So it needs to be easy to understand. And the third one, as I said, we will try to revise the code, extend the code, and change the code in some way to do more jobs or change the implementation because maybe the requirement changes or we know more about the domain, so why you want to change it. So it has to be easy to change. So in a sense, a good written, well-written kind of code, a piece of code should be fulfill these 3 points, right? Of course, nowadays you can always ask AI any kind of large language model the same questions, right? So I have tried to ask DeepSeek, what is a good program? And also ask AI to generating a simple function, a Python function to calculate the factorial of a long negative integer. As a reminder, this is the equation to calculate this, right? So the answer given by DeepSeek looks like this. It emphasizes it has to be correct. That means it do the right job, right? Do the job. And also it has to be efficient. It needs to be fast enough, right? Efficient means both in time, but also space. A lot of computational kind of task we are handling in wind energy, which can be very heavy. Like if you want to do a high fidelity simulation of a floating wind farm with the interaction of the flow, aerodynamics, and also the hydrodynamics and everything taken into account, that's time consuming. It will take a lot of CPU time, but also space, right? If you are working with nowadays, data-driven model, you will need to handle a lot of temporal, spatial kind of time series. All of these needs to be considered, right? So it also needs to be readable, as we have emphasized before. It also says that it has to be more modular. This is a way kind of enable it to be easy to change in the future. If you design your system or your software or code into a modular different subsystems, subcomponents, So it will be much easier to maintain in the future and also to extend in the future, right? It also talks about the robust, so handles errors and edge case gracefully, and also talks about the documentation, which in a way is also a core part to improve the understandability of a program, right? So if you know Python already, you can recognize this function, which is doing a job to calculate the factorial of a integer, right? And if you say, yeah, first of all, you can notice that the AI generated code has a lot of docstring and comments, right? It's properly written there to explain what the code is doing. And also, it has some edge cases handled, right? If so, there's also a value error here because the definition of factory only works for positive or non-negative integers. So it has this edge case. If it's negative, it'll read this value error, right? So this is a nice example for AI that can generate a nice kind of program as an example for us. But of course, our problem is not just writing a simple function. So that's also why we think we need to know more and also have more experience in this domain. There can be many different concepts or practices that we should know, but just to put the most basic or most essential ones, or at least the three aspects here. As you can see, first is about the readability. So it's the same thing as easy to understand, right? Easy to read. So it can be different ways we could accomplish this. The first thing we emphasize, but a lot of time, a lot of people don't pay attention to is about the naming, right? Just the name your variables carefully. So it should be meaningful, should be easy to understand what is this variable stands for. Instead of A, B, C, or X, Y, Z, maybe we just say count in wind speed or count out wind speed. So we can know very clearly what this variable stands for. And also regarding the modular design, we need to use functions, right, as a basics, using functions to enable us to reuse the same operation, right? But also using modules, classes, and maybe we'll also build our own libraries or the other structures in the programming language we have. And of course, comments and documentations is a critical part. I think especially for the scientific programming we are handling, sometimes it's really necessary to add more comments, especially if you are, let's say you are implementing a model or a specific model or from let's IEC standard or something, then you should put the source there, right? So that later people can refer to this documentation. Yeah, what do you mean? If you are using a specific version of an equation, maybe you should refer to the book, to the paper, to all the sources. This makes later kind of extension much easier, right? Also, people can check that. And the other thing is about reproducibility and the maintainability, right? So, of course, we should use version control, which is also a critical part to allow us to track all the changes, different versions, and also allow us to collaborate with others kind of over the same code base, right? And of course, we should avoid hard coding on all these things. These to be considered. And the third aspect I want to emphasize is the efficiency and the validation, right? Efficiency in a lot of situations is critical because if it's not fast enough, if you want to do design optimization over a very slow simulation or model, that's kind of infeasible. If one simulation takes weeks, then how many different choices are you going to afford to compare with, right? So this needs to be considered. And also, before all this speed, kind of we need to make sure it's right? So that means we have to consider test rigorously, right? And also one thing I want to emphasize is that we have to be careful. Don't don't do premature optimization. There's a famous quote in computer science which says premature optimization is the root of all evils. That means if you you have to make the code right first, but then you just pay attention to optimize everything, make it super fast. But then if the results is wrong, all of this is meaningless, right? So consider that. So now I think Jenny will give us some solid examples what we mean by all these different good practices.
Yes.
Yeah.
Okay. All right. So I think I have 3 examples of kind of how some of the concepts that Jufeng has just explained you can actually put into your code. One of the first things I wanted to talk about is something that I don't think that engineers are ever taught. So it's testing. You can write tests for your code, and what you should be doing is writing the tests, and then leveraging existing testing frameworks. So I wanted to give a short example of what is a test, what does that look like, and just to kind of give an example of that. So let's say that you have a simple function. I will be using Python here, but it's pretty readable even if you haven't had Python. So hopefully this makes sense. It's a very simple function. It takes 2 things and it returns the multiplication of the 2 things. So naturally we should think, okay, let's try to make a test of this function. What does a test look like? There we go. Our first simple test would just be a test in essence is giving particular inputs with a known output. So I know if I multiply 3 times 4, I better get 12 or something is very wrong, right? So we write a function that is a test function, and it's using something called an assert statement, which in this case just means that if the stuff that comes after the assert statement is false, it will raise an error. In other words, the test will fail. So here's a very simple test to make sure that my multiply function in a basic way is working as I expect. But we can actually dig a little bit deeper and we can think about more interesting test cases. So going back to what Jufeng mentioned about handling edge cases or failing gracefully or things like that. So even within just integers, I only had 2 positive numbers, but I should also check a positive and a negative, right? Make sure that that's working out. I should check a negative and a negative, make sure that's working out. There are more elegant ways to do this using PyTest than what I have here, but I wanted to keep it simple, so I just put multiple assert statements. So immediately we've already increased the robustness of our code by adding more test cases and trying to be a little bit more creative with what sort of inputs might we expect from a user. We can even go a little bit more interesting. We were doing integers, but maybe we also expect floats, right? And floats and integers are stored in computers differently. So you need to test them a little differently as well. And now we have to do something maybe a little tricky where we need to use this NumPy function to check that floating point numbers are acceptably close to machine precision. So already our code is getting a little bit more interesting, a little bit more robust. And then maybe we do something that's really weird, but could be useful, which is what happens if I multiply an integer times a string. It just concatenates the strings together, but maybe I want my function to do that. So then I need to write a test to make sure that my function is behaving in that way as expected. Or maybe I, as a designer, decide that my function should actually not accept this, and then it should raise an error saying, hey, you can't take those as inputs or something. So in general, going back to kind of what Jufeng was mentioning, understandability, modularity, thinking about your end user. How is someone going to use your code? Your end user might be you in like a few months, but you should be thinking about that. What is some way that you might use this function in a different context? Another example of, how can we already do something a little concrete? This is with the file structures. How do you arrange all of your files in different ways? What is a way that can, assist with this bit about understandability, maintainability, and then efficiency as well? So here's an example of files that could be on a GitHub repository. I'll explain a tiny bit more about that on the next slide. And this is kind of one way that you could do this. I'm not saying this is the perfect way. There is no perfect way. This is just an example of what you could do. So what you could do is say in this, it's currently called examples, but the folder could maybe also be called scripts. And the idea is that this is where you put code that is meant to generate something. It does something, it makes a plot, it calculates some results, it does post-processing, something like that. But the idea is that these scripts that are here in examples, they should be calling upon functions, classes, things like that that are defined in some sort of source package. Ideally, this would be like in Python, it would be a Python package. So going back to the concept of breaking your code down into reusable chunks, you should think, okay, I just wrote these 30 lines of code in a script, but it's something that I want to reuse in another script. As soon as you're thinking about doing that, you should probably turn that into a function that is getting packaged, right? Or a class, depends. Then you can have some input data, maybe. You could have some output data. Maybe these aren't tracked in your GitHub history. Maybe they are. And then you can have a whole subfolder for tests as well. So this is where you can store your tests that are checking that the functions and classes and stuff in source are working correctly. So already this is kind of organizing your code and making it maybe more easier for someone to understand. And there's some other files down here I'm not really going to talk about. I think the last thing I wanted to mention was Git and GitHub. This is another thing that I don't really think engineers are explicitly taught in general. Of course, there are exceptions. But my 2 cents is that if you are collaborating on code, like if you're writing code in a team, which in Denmark, it's very common to do assignments in groups, knowing how to use Git and GitHub, it's essential. It's a pity that it's not taught because it is essential. It is also, I would say essential, but maybe that's just my personal opinion. It is extremely useful, even just by yourself. So what is it? It's essentially, this is very quick introduction. It's version control software. So it allows you to track changes in your code. If you need to go back because you made a bad implementation and you want to undo it, you can do that, but like without losing all of the history along the way. If you want to kind of jump into a parallel universe and like try to develop some code and then it works and then you want to bring it back into the main universe, you can do that using branches. It handles merges very nicely. Well, except for merge conflicts, but it has the ability. So this is all just on your computer. And then GitHub is essentially the online hosted server. So that allows different people with different computers to kind of sync to the same repository online. And GitHub allows kind of this collaborative aspect where you're using things called pull requests to like review each other's code and then merge it in when it looks good. Things like that. I will be honest, there is a learning curve to it, but it is worth it. So I would highly, highly recommend like learn how to use this. If you're working in a team, push your team, figure out how to work it. We also offer trainings in it, so talk to us if you want. But that would be my number one recommendation, I think. Yeah, that was it from my side for now on the practical stuff.
Yeah. I think as you have mentioned, even if you are working alone with your own code, it still benefits a lot from using version control, right? So all of these kind of practices and tools is essential. But even before all this, we need to kind of think about, right? How do we solve the problem, right? So this is I want to talk about the computational thinking, which is now a popular term. It's first made popular by Janet Wing, and she said that computational thinking is the thought process, right, involved in formulating a problem and expressing its solution in such a way that a computer, human or machine, can effectively carry out. So notice here in this sentence, compute means both human or machine, because that's the original meaning of computer. Someone computes, right? So if we think about it, here it's really emphasized, first of all, is the thought process, right? It's just about thinking. How do you think about your problem, right? How do you formulate it? And it's also emphasized about how do you do the problem formulation. As we may know, experience in mathematics, right? If you have sometimes it's like magic, right? So some problem, if you do some transformation, some kind of the right formulation will make the math easier to solve, right? In certain domain. And also in this way, so if we want to use computer or algorithm to solve some things, you need to formulate it in such a way so that it can be solved. Now, of course, the third thing is to express your solution in such a way. Usually it's like code or algorithm we write, right? How to solve it. Of course, in the end, you need to write the code and run it, right? So actually solve it. And all of this is essential kind of prerequisite before you can actually writing your code, right? And there are different kind of code concepts, but I want to emphasize 4 here. One is abstraction. The other is decomposition. The third is pattern recognition. And the fourth is algorithm design. So abstraction means that we need to have a right kind of simplification to the problem, to formulate in a way that we could focus on the essential part, right? It's like in physics, we have this concept of mass point, which ignores all the geometry, all the size, all the other features of an object, but just the mass, right? Which is kind of a way to simplify, but it's very useful. And also the other thing which we will use a lot in different computation domain is decomposition, especially for software, complex software. You need to decompose your problem into smaller and hopefully also modular ones, right? So that you can manage and solve them independently. And of course, pattern recognition means that we need to identify the similarity between different kind of subprograms to be able to relay and reuse some solutions before, right? And all of this is to be translated in the end into a step-by-step instruction, which in a sense is the algorithm to actually solve the problem, right? So we could say if we're facing a problem, we want to first specify the problem. We could using abstraction, decomposition, or pattern recognition to find the right kind of formulation. Then we write the algorithm or the instruction step-by-step kind of workflow, right? What do you want to, how you're going to solve it. And then actually implement the solution and evaluate. And hopefully it can also be generalized later for other problems, right? So of course, ideally, this will be sequential step-by-step, but in reality, everything is kind of iterative. You have to go back to redo something, revise, update all this, right? So, and there are different kind of approaches you could use. I will not talk about these specific slides in the favor of time, but you could check later. This is also from this book, which is interesting, I think, if you can read it. So now I want to talk about the scientific programming, which is kind of essential for a lot of engineering domain, but is of course also for wind energy, right? So it's basically the practice of using programming and computation tools to solve scientific, engineering, and technical problems. So it means we have to write code to analyze data, typically simulating some physical phenomenon, some system, model some phenomenon, and also do the visualization of the results, right? So that we can get some insights. We can take some actions, right? That can be useful. Typical kind of operations we will need to do can be scientific computing, like data analysis, we do modeling or simulation, and also we do optimization, right? If you want to improve the design or improve the control strategy, we typically want to solve optimization problem, right? Like if you want to investigate, yeah, how should we design a wind farm in this specific location? Where should I place all these turbines, right? It needs to be formulated, or it can be formulated as an optimization problem. Then use some tools or scientific computing code to do the job, right? And then, of course, visualization is also a very useful aspect of scientific computing, right? And also a lot of time it just helps us in automation, because we can sometimes we put all this repetitive tedious work. If we want to automate it, it will help us to reduce the workload and also avoid all these errors, right? Which can be very frustrating. And in Python, because we are using Python in our courses, and we also think Python is a really good kind of starting language for scientific programming. It has a lot of kind of open source library that can be very useful, like NumPy. This is kind of operation on different matrix arrays, right? And also different functions provided, the basic kind of mathematical functions, which you can just use. And the core of NumPy is in C, so the speed-wise is also highly efficient. And of course, also SciPy is if you want to solve some equations, right? Like some ODE, ordinary differential equations, or if you want to do some simple optimization, it also provides the tools to do all this. And typically in scientific computing, we do a lot kind of interpolation or extrapolation. All this is handled by SciPy. So the most very basic one for visualization is the Matplotlib, which is also in Python, is widely used. So it's also kind of a core library. Everyone, if you're using Python for scientific probing, everyone should also know this, right? Must all this. Yeah, but you may ask, we know it's important, we know it's kind of critical, but how do we actually developing all these skills, right? If we want to be able to write good code to solve the complicated, complex problem we're facing. So in our kind of a philosophy, we think the best way to learn something is to learning by doing, right? But also we emphasize you need to thinking. To pay attention to the thinking process, like what we mentioned about computation thinking, right? So in a sense, we think the best way to learn something, but specifically for scientific computing, is to reading, thinking, and doing. What do we mean by reading and thinking and doing is like this, right? Reading in this context can be you read some books, right? But you also can read some code, some other code, like open source library, like NumPy, all these other things, like also the PyWake, Top Farm repository, D2Wing has developed, right? So reading all this code is a critical part, but also you need to think, why do they do this? How, if you are going to do the job, how are you going to attack the problem, right? But of course, all this without actually doing the job, without actually coding is kind of superficial what you are going to learn, right? So you have to actually practice the coding part, the writing part, right? So like Confucius has said, learning without thought is laborious. Thought without learning is fruitless, right? So that means we need to really to think about how to code, but also very importantly to actually to doing the job, right? And of course, in our domain, in wind energy or any engineering domain, we're trying to solve problem, right? So it's actually kind of all this workflow. First, we need to understand what a problem we are facing. We need to have a plan, devise the plan to solve this problem, but we need to carry out the plan, right? And also we need to reflection. All this kind of, it goes iteratively. In our domain, in our field, we could say you need to understand your problem. You need to have a kind of the thinking divided into different component, different problem, and have a plan, and then actually to write the code and also be able to reflect, looking at the results and reflect what can be improved. Maybe something's wrong, you need to change, and all this is essential. So for us, we think what we really need to be able to effectively using scientific programming to solve the challenges in wind energy, we need to both know the domain, the wind energy part, we also need to know the numerical part, and also most importantly, very importantly, is the programming, the actually coding part, right? Which is nowadays largely missing in a typical training of an engineer. So that's why we think we really need a proper training in scientific programming and software development, right? And how best to develop all this, of course, is by hands-on coding works, right? So in a sense, we think the best way to learn programming is, of course, just programming. So that leads us to the coming course, which is the scientific programming for wind energy, the online course for the online master, right? It's coming in September this fall. It will be a 13-week online course. But now you can already, I think soon you will be able to register for this course, right? You can find all the more details in the link. But here is the learning objective, right? We want to really emphasize we're using Python for this course, but we are truly want to emphasize is the general part, right? The good programming practices, the foundational tools like the Git, like VS Code and all these things. But also we are going to kind of emphasize to actually to do the job, to write functions, classes, libraries, and all these things for a specifically defined wind energy related application, right? And also we want to teach or help you to gain a skill to be able to analyze your problem, to write and debug, write tests, and also communicate your code, right? This is the focus of this course. And we have a kind of the plan for these modules looks like this. So it's covers both the basics part, but also more the part 2 will be focused more on the scientific programming part. And the part 3, we try to emphasize so that we can also know some more advanced topics like objective-oriented programming, and also how should we design our complex system or our software, right? How do we design the architecture and all the thinking behind it? And all of this, in the end, will be combined in a Philo project. We will provide several kind of predefined project for you to choose, but you may also choose your kind of define your own. But in the end, we want you to be able to learn from the basics and all the way to the high, more advanced topic, and that enables you to be able to write your own kind of software for your kind of problem. So keep in mind, so we also cover the basics. So this course is also, even if you have low or very few experience with programming before, so don't be afraid. If you are willing to devote more time and efforts, you will be able to gradually kind of climb the hill and be able to do a lot of better things in the end. And yeah, Jenny, you can also introduce about some other learning opportunities we have, right?
Yes, I just wanted to say towards the end, we mentioned that there is this Master of Science course. So I just wanted to kind of explain a bit what is the difference between the online master course, which is happening in the fall, and the Master of Science course, which happens in the spring. So yes, first things first, there are different semesters. If you're interested in looking into the Master of Science, I have some links here. I think you can also Google it. And we do have the course material for that course up on GitHub. So you can look at that if you want. So the main difference, this is Master of Science program course, in the spring. It is part of the Master of Science here at DTU. In particular, it's aimed towards the students in the wind energy Master of Science or in sustainable energy or sustainable energy systems. We do offer both physical and online attendance for this Master of Science course, whereas the online master course is tailored specifically to online students. And the content is also a little bit different. So for this Master of Science course, we honestly don't really teach fundamentals. We kind of assume that students can pick that up in the space of the course. And there's a much stronger focus in coding in teams because that's what our students need for their Master of Science programs. So I just wanted to let people know that's the difference between the two of them. And then the other thing I saw there was in the Q&A, Emilio pointed out that we've done this GitLab seminar or GitHub. So we can also, if there's a company or an organization that wants, for example, a 1, a 2, a 3-day course in a particular topic, we do have the ability to kind of condense it. So if the idea of doing a full 13-week course is too intensive, if you have enough people, you might be able to arrange like a shorter lifelong learning module with us. So please don't feel free to hesitate. Feel free to reach out to us if that sounds interesting. Don't be afraid. So yes, I think that's what I wanted to say. Perhaps a little more eloquently, but here we go.
Yeah, thanks. I think that's it. Thanks for all who attend this masterclass. And if you have any questions, let me check. I think now it's time for questions.
Yes. Thank you, Zhifeng and Jenny, for the really inspirational presentation. So I can see there's some questions in the chat. By the way, if you have any questions, please write in the Q&A because we cannot because of the copyright issue, so we cannot allow you to speak. So we have questions about PyWops. So are you guys going to teach PyWops libraries in your course?
No. I think if you are interested in PyWasp, you should contact the WASP team. Maybe they will offer lifelong learning for you. Yeah.
Yes. Okay.
PyWin. What do we mean by PyWin? Okay.
Yeah, there's a question about PyWin also.
Maybe PyWake?
PyWake, yeah. Yeah, we will not specifically teach you on PyWake, but you may use it, right? So maybe in some project you could use it. If you have questions specifically on that, yeah, we could answer your question.
Okay, thanks. Yeah. There's a anonymous attendee. He asked, which Python packages tools would you recommend as the most suitable for energy system modeling?
Yeah, energy system modeling, I think it's an active field, right? So unfortunately, Jenny and I were not expert in this aspect, but I know that there are some open source kind of tools there to do the job, right? So you need to be, but as I said, this course is about kind of fundamental, right? Foundational. If you have a good experience, you should be better kind of understand the existing options and use it for your purpose. And also you may want to extend or modify an existing kind of library for your specific need, right? So that's why we don't really focus on specific kind of aspect or a domain, but we want to emphasize if you master the basics, you will be able to do a much better job to use the existing or extend the existing tools, right?
Yeah. Okay. Next question. There's a attendee asking, after completing this program, will he get a master degree? Yes, you will get a Master of Wind Energy degree. So that is a 60 ECTS degree. So it's a bit different to the Master of Science degree. Master of Science is 2 years, so it's physical, so it's 120 ECTS. But with a Master of Wind Energy, that is a part-time degree, so it's completely online. That consists of 60 ECTS, so it's half of what Master of Science is. Next question, Stefano, he's asking about, will you guys teach any programming regarding the wind related application in your course?
Yeah, I think all the assignment, all the kind of project work will be kind of wind energy related, right? Like we could have you building a wind turbine model based on BAM theory. You could have a kind of a wind farm simulation optimization, or something also related to kind of a wind power forecasting, all the things, or wind resource assessment, right? But the important thing is we want the students to be able to do is to given a question, given application, how would I write my own code to do that, right? Maybe using some existing library out there, but you need like part of your code to combine them, or how are you going to do that, right? So this is, we think, is the important skill.
Yeah, thank you. And yeah, some people asking if we will share the recording and slides. Yes, we will share it. Yes, after this masterclass, we will send it to your email with a link. Yes, next question from Laura. She's asking if there are any specific libraries that you will be taught in the course, like Forest.
Yeah. Forest is similar like Pywake, right? It's open source steady-state wind farm simulation tool. So I guess there's also previous one someone asked about do we have any courses on Pywake, right? So I think in general, if you have a need in specific tools or software DTU Wing is offering, you can always contact us so that we can provide a specific or tailored training to you, right? And also for the wind farm modeling in general, maybe this course, of course, is not focused on wind farm modeling specifically, but yeah, we could imagine maybe developing some other courses for your lead, right? If we have sufficient number of people interested. Yeah.
Yeah. Okay. So there's a question about the ECTS. So for this online master course, this scientific programming for wind energy, so it's accredited. This course is in an accredited program, so you will get 5 ECTS after completing the course. But for the course on Coursera, you won't get ECTS. Yeah. And next question is a follow-up question from Stefano. He means that wind-related application is that one could expect it to work on in the course.
Yes. I think we can, of course, provide multiple kind of assignments that you may choose from, right, depending on your specific interest. But like what we have did for the Master of Science course, the final project, we provide 3. One is on the wind turbine modeling, one is on wind resource assessment, and one is on wind power forecasting, right? So definitely all the examples, the assignments, the final project will be wind related. And we may also provide multiple kind of choices for the students yourself to choose.
Okay, thanks. And one more question. Is there any planned course on Pywake in the coming months? And yes, if we see there's a demand for a course in Pywake, then we will develop it. Yeah.
Yeah, if there's sufficient demand, I think we could also have an online master course for wind farm modeling in general, right? Which can cover Pywake or Flores or also other tools.
Yes. Yes, we have a similar course about
wind farm planning, right?
Hawk
You have
2 and warps and
yeah.
and also ellipsis. So we have a course called numerical tools. So it's about the Hawk 2. So it's about but it's not about PyWake, not yet.
Yeah.
But if enough people are interested, Alan, would it be possible to add PyWake as an option to that course? Yeah, because students choose like one of the tools, right? And they get to learn the tool of their choice, if I remember correctly.
That's possible, yes.
Mm.
Yes, if we see enough demand, yes.
Yeah, okay.
Yes, there's some questions about do we work on integrated energy systems? Yes, we have courses, and also we have a whole division of people. They are working on integrated energy system like wind farm and how does the grid connection to the wind farm, how does it behave, and also we have courses about this, and also we have courses about hybrid power plant. So we have solar panels and how does it connect to the wind farm and battery. So we do have a lot courses that we offer about in this direction. Yes, I think that's all the questions we have mostly. So okay.
There's a question make wind forecasting for 20 or more years. Oh yeah. That's a really good research question, I would say.
Yes.
If someone can do it accurately, that would be amazing. But I think the challenge is huge, right? Yeah.
Yes. Yeah. Next time we can invite some expert from this area to the masterclass.
Yeah, it's more like the climate forecasting, right? If you want to forecast in the 20 years, what would be yeah. I think it's in general a very interesting question. Yeah.
Yeah. Okay. So
There's
for the
also,
time
I think
being,
there's also one question on the Python aspect. Someone asked about will the Python skill be used in other courses, right? I think in online master program there are many courses that has programming aspect, right? Do they typically using Python or? I think most of them are using Python nowadays.
Yeah, some courses quite a lot of courses. I think almost most courses they use Python. So you will be benefit from taking this scientific programming course. Yes. Yes.
Yeah.
So okay. So for your time being, so once again, thank you, Zhufeng and Jenny for accepting the invitation, and also thank you everyone for attending this masterclass. And we will have another masterclass, I think in June. So please stay tuned. And thank you, and have a good evening.
Thank you. Thank you all for
everyone.
attending. Bye.